Welcome back to the Deep Dive. Today we're embarking on, well, a fascinating exploration into a truly powerful area of chemistry. It's one that's really fundamental to creating countless modern advancements, from life-saving medicines to the materials that build our world. Forget the dense textbooks. Our mission is to extract the most important insights, those aha moments, and really connect the dots for you, our curious listener. We're talking about the world of transition metals in organic synthesis. If you've ever wondered how scientists build incredibly intricate molecules, or how they precisely attach specific pieces to create entirely new compounds, or maybe how they do it efficiently and sustainably, then this deep dive is definitely for you.
It really is a realm of precision and elegance. Today, we're zeroing in on two of the most widely used transition metals, copper and palladium. And what makes them so special is, well, their ability to act as catalysts. Unlike some chemical reactions where you need, a large equal amount of your starting materials and reagents, many transition metal reactions are catalytic.
Catalytic, right?
Which means a tiny, almost microscopic amount of the metal can facilitate the creation of a vast amount of product. Imagine like a single master key opening millions of doors. That's sort of the power of catalysis. And it has massive implications for both industry and the environment.
Okay, so our journey today is to demystify these reactions. We'll explore how these metals act as silent, powerful partners in chemical transformations. We want to understand the key steps in their catalytic cycles, including concepts like oxidative addition and reductive elimination, and see how changes in the metal's electron state are crucial to their magic. We'll break down the major reaction types, synthesis strategies, practical applications, making sure every technical term is, well, explained along the way. Think of it as a backstage pass to some of the most elegant chemical orchestrations. Okay, let's unpack this. First up, copper. Now, when we think of copper, many of us might picture pennies, electrical wires, maybe even the Statue of Liberty.
Sure, the common stuff.
But in the world of organic chemistry, copper takes on a completely different role. Here, organocopper compounds are incredibly prized tools.
They truly are. The story of their synthetic application got a significant boost from studies on how copper dramatically changes reactions of Grignard reagents.
Grignard reagents. Yeah. Okay, refresh this quickly.
Right. For those maybe not in the lab day-to-day, Grignard reagents are essentially supercharged carbon atoms, really eager to form new connections. Think of them like molecular construction crews ready to build carbon frameworks. Now, without copper, these Grignards often add to a molecule in a very direct way. Let's call it a head-on collision or Levern-2 addition.
Okay, direct attack.
Exactly. This is where the Grignard carbon attacks directly at the most obvious electron pore spot, often leading to an alcohol after workup. But here's the aha moment. Just a catalytic amount of copper can completely redirect that reaction.
Just a tiny bit.
A tiny bit. Instead of that head-on collision, copper guides the Grignard to a side swipe, or conjugate addition, also called 1-mofo-4 addition. The attack occurs further down the chain at a different carbon atom.
Oh, okay.
And this leads to a completely different and often more desired product for synthesis, usually a saturated ketone after you process the reaction. That tiny bit of copper completely redirects the outcome. It's quite amazing.
That is remarkable. Just a little copper changes the whole game. So how are these incredibly precise organocopper reagents actually made?
Well, they're primarily made by reacting organolithium compounds. That's another type of supercharged carbon reagent with specific copper salts, usually copper I salts, and the ratio in which you combine them is absolutely critical.
The ratio matters.
Big time. If you use a 1.1 ratio organolithium to copper salt, you usually get what's called a polymeric alkyl copper. Think of it like a tangled, often insoluble mess. It's generally less synthetically useful because it's difficult to control its reactivity.
So a bit like a raw, untamed material rather than a fine-tuned instrument.
Exactly, that's a good way to put it. But when you use a 2.1 ratio, 2 parts organolithium to 1 part copper salt, you create what are called cuprates, specifically diol cuprates.
Okay, cuprates, these are the important ones.
They're the true workhorses, yes. The copper in these species, it's copper, has all its relevant electron orbitals filled. It's a D10 configuration. This makes it incredibly electron-rich. And this high electron density makes it a remarkably soft nucleophile, which we'll unpack in a moment.
Soft nucleophile.
And these cuprates, they aren't just simple static molecules floating around in solution. They're dynamic, sort of shape-shifting clusters. For example, a common one, lithium dimethyl cuprate, often exists as a dimer, meaning 2 units linked together.
A dimer.
Yeah, it can form something like a tiny tetrahedral cluster of lithium and copper atoms. And this incredible adaptability, the way they can form different arrangements, aggregates, is precisely what allows chemists to fine-tune their reactivity with, well, almost surgical precision. Even larger aggregates have been observed, and they definitely influence how these things behave.
It sounds like understanding their exact form in solution is really key to predicting their behavior. And you mentioned mixed cuprates. What's the advantage there?
Mixed cuprates are a huge advancement. Imagine you've spent a lot of time, maybe weeks and effort, synthesizing a complex, valuable organic group.
Right, you don't want to waste it.
Exactly. You only want that one specific group to react. Mixed cuprates allow you to do this. They have two different ligands or groups attached to the copper. One is your valuable organic group, the one you want to transfer. The other is a dummy or non-transferable ligand. Things like copper cyanide can be involved, or maybe a sulfur-containing group. This dummy group preferentially stays attached to the copper, so only your valuable group gets transferred onto the target molecule, saves you precious material.
That makes a lot of sense, conserving the important piece.
Precisely. And a particularly important type of mixed cuprate is the higher order cyanocuprate, prepared using copper cyanide. They're known for enhanced stability. And interestingly, in these reagents, the cyanide group doesn't seem to bind directly to the copper itself, but rather to the lithium ions that are part of the cluster, often forms a unique ring structure in the dimer.
That's complex.
It is. But these are excellent for selectively transferring valuable organic groups. For instance, if you have a mixed methyl-alkynyl cyanocuprate, only the alkynyl group that's the one with a carbon-carbon double bond will transfer. Incredibly selective.
Wow.
And we can even prepare these starting from alkynes using clever techniques like hydrazirconation or by swapping metals with things called alkynyl stannins. Lots of ways in.
Are there other paths to make these organocopper reagents, especially if your organic molecule is maybe a bit sensitive?
Yes, definitely. Sometimes your desired organic molecule has other delicate parts, functional groups like nitro groups or esters, that would react with those powerful organolithium reagents we just mentioned. They'd get destroyed.
Right, they're too reactive.
Too reactive. So in these cases, we can sometimes make organocopper reagents directly from the corresponding organic halide and very reactive copper metal. This supercharged copper metal is made by reducing other copper salts. It allows us to prepare organocuprates with sensitive functional groups intact.
That's useful.
Very useful. And you can even generate them in situ, which just means right there in the reaction flask, by simply adding a catalytic amount of a copper salt to a Grignard reagent. Saves a step, makes the whole process more convenient sometimes.
Okay, so these organocopper compounds are quite versatile in how they're structured and prepared.
Yeah.
But what makes them such essential tools? What's their unique superpower, chemically speaking?
Their defining characteristic, really, is that they are superb soft nucleophiles. This is a crucial concept.
Soft nucleophile. Explain that a bit more.
Okay, imagine a nucleophile as an electron-rich species, maybe like a magnet, eager to find and attack electron pore spots on other molecules. Now, a hard nucleophile, think of a simple Grignard reagent, again, might just smash into the most obvious, most positively charged electron pore atom, like the carbon in a carbonyl group, CO. Very direct.
The 12 and 2 addition we mentioned.
Exactly. But a soft nucleophile, like an organocopper reagent, is more subtle. It prefers to attack carbons that are already partially bonded within a larger system, like part of a double bond system, especially one conjugated to a carbonyl, rather than a highly polarized spot.
So it attacks further away.
Often, yes, in conjugated systems. This preference allows for incredibly specific and synthetically useful reactions, really setting them apart. Their most important reactions involve replacing halogens or similar leaving groups, opening up strained ring structures called epoxides, and performing those famous conjugate additions to molecules with a double bond next to a carbonyl.
Right. Let's dive into those reactions then, starting with how they handle halides and these other leaving groups like sulfonates.
Certainly. A real breakthrough discovery by chemists Corey and Posner showed that a specific copper reagent, lithium dimethyl cuprate, could effectively swap out an iodine or bromine atom for a methyl group. And it worked on a wide variety of molecules, including those with aromatic rings, like benzene rings, or double bonds attached to the carbon bearing the halogen.
So it's very general.
Very general. And it typically gave much better yields than older methods using just Grignards or organolithiums for these specific swaps. It was a game changer. Now, when these reactions happen on, say, secondary carbon atoms, carbons attached to two other carbons, they often proceed with a precise inversion of stereochemistry. The 3D arrangement flips like an umbrella in the wind.
Okay, inversion. That sounds like a specific mechanism.
It is. It's a classic sign of an SN2 type reaction mechanism. But for aryl and alkynyl halides, where the halogen is directly attached to an aromatic ring or a carbon double bond, a direct SN2 reaction just isn't feasible geometrically.
Like the backside attack is blocked.
Exactly. So here, the copper performs a kind of two-step dance. First, there's an oxidative addition where the copper inserts itself into the carbon-halogen bond. The copper essentially increases its oxidation state to copper temporarily. Then a reductive elimination happens. The two organic pieces that are now attached to the copper come together, form a new carbon-carbon bond, and the copper returns to its original copper state, ready for another cycle if it's catalytic.
So the copper acts like a temporary matchmaker or a bridge, bringing two different carbon fragments together that wouldn't normally react.
That's a perfect analogy. It forms a temporary connection, enables the two organic groups to find each other and bond, and then gets out of the way. Now, for allelic systems, these are molecules with a double bond right next to a carbon that has a leaving group, like a halide or acetate. Organocopper regions often give a product where the double bond has shifted its position.
Ah, the double bond moves.
It moves. This is called an SN2 reaction, SN2'. And what's fascinating is that chemists can fine-tune these reactions. Just by changing the solvent, say from ether to THF, or by adding small helper molecules, you can push the reaction towards a specific outcome, either substitution at the original site, SN2, or substitution with that double bond shift, SN2. It allows for exquisite control.
You can really see how chemists can fine-tune these reactions just by tweaking the conditions, leading to very specific desired products.
Absolutely. And this precision extends to stereochemistry, too. In cyclic systems, like cyclohexane rings, we often see a strong preference for anti-stereochemistry.
Anti, meaning opposite sides.
Exactly. The new group adds to the opposite face of the ring compared to where the leaving group was. This is often dictated by the molecule's preferred three-dimensional shape, which sort of guides the incoming copper region to attack from the less hindered face. Even the presence of a nearby oxygen atom can direct the addition. Sometimes it reinforces the selectivity, other times it can even reverse it, especially if the oxygen can chelate or bind temporarily to the copper or lithium.
Wow, subtle effects.
Very subtle. And propergelic systems, those with a leaving group next to a triple bond, they react in a unique way too. They often transform into interesting molecules called allenes, which have two double bonds right next to each other.
Okay, so substitution covered. Let's move on to another vital transformation. The opening of epoxide rings.
Right. Organocopper reagents are excellent at opening epoxide rings. Epoxides, remember, are those strained three-membered rings containing an oxygen atom, COC, in a triangle.
Strained, so reactive.
Exactly. The copper region acts as a nucleophile, attacking one of the carbons in the ring, which then breaks open, relieving the strain. Crucially, the attack almost always happens at the less hindered carbon atom, the one with fewer bulky groups attached. This regioselectivity is incredibly useful synthetically for setting up precise molecular structures.
Predictable outcome.
Very predictable. The reaction also happens with predictable transdiaxial stereochemistry in cyclic epoxides, like those based on cyclohexane. This means the new group that adds and the resulting alcohol group end up on opposite sides of the ring and pointing up and down, axial. This level of control makes these reactions invaluable for building complex molecules with specific 3D shapes. And what's even more interesting is how they react with epoxides that happen to have a double bond attached nearby, sometimes called vinyl epoxides.
Okay.
Here, the alkylation, the addition of the new group from the copper region, often happens at the double bond itself, coupled with a shift of that double bond, and the epoxide opens up. You end up with a molecule called an allylic alcohol. It's a bit more complex, but very useful.
So we've seen copper is great for these precise substitutions and opening epoxides, but its real fame, I think, comes from conjugate addition reactions, often called 1004 additions. Can you tell us about those?
You're absolutely right. This is where copper truly shines as that quintessential soft nucleophile. Imagine a molecule with a carbon-carbon double bond directly next to a carbonyl group, ACOO. We call this an unsaturated carbonyl compound, or an anun if it's a ketone. It's a conjugated system.
Conjugated.
Okay, now a hard nucleophile, like our Grignard again, might attack the carbonyl carbon directly. That's the 12 or few addition.
Head-on collision.
Right. But a copper reagent, being soft, prefers to attack the carbon at the end of that conjugated double bond system, the Vo carbon, which is technically 4 atoms away from the oxygen if you count around.
1,4 addition, that's where the name comes from.
Exactly. This is 1,4 addition, or conjugate addition. It forms a new carbon-carbon bond at that bubba position and temporarily creates an intermediate called an enolate. And over the years, chemists have found really clever ways to make these conjugate addition reactions even better, even faster, even more selective.
Like adding things.
Yes, adding simple compounds like trimethylsilyl chloride, TMSCl, can dramatically speed up the reaction. Sometimes it even traps the intermediate enolate that forms, making the whole process cleaner and more efficient. Even adding specific Lewis acids, like boron trifluoride, BF3, often complexed with ether, can interact with the copper reagent, making it even more reactive for conjugate addition.
So it's not just the copper.
It's rarely just the copper. It highlights that it's often an intricate dance between the copper reagent itself, the lithium ions that are usually present, various additives like TMSCl or BF3, and even the solvent that dictates the reaction's success and speed.
It sounds like a very sophisticated chemical choreography. What's actually happening at the molecular level in these conjugate additions? Can we peek inside that black box?
We can, thanks to computational chemistry, basically using powerful computer simulations to model the reaction pathway. It allows us to see intermediates and transition states that are impossible to isolate.
What do the computers tell us?
For conjugate additions, the computation suggests it starts with the copper reagent and the starting molecule, the anon, forming a tight complex. Often the lithium ion helps coordinate the carbonyl oxygen. Then, a crucial intermediate is formed, possibly involving that higher oxidation state, copper, where the new carbon group has added to the fosco. This intermediate then undergoes the reductive elimination step to form the final carbon-carbon bond and regenerate the copper species. Now, what seems unique here compared to some other copper reactions like SN2 substitution or epoxide opening is that this final bond-forming reductive elimination step is often the slowest part of the whole process. It's the rate-determining step.
So speeding that up is key.
Precisely. Speeding up that specific step is key to making the whole conjugate addition reaction faster. And for example, our computational models show how BF3, that additive we mentioned, significantly stabilizes the crucial transition state for this rate-determining reductive elimination.
Okay, so it helps the final step happen.
It seems to actively help that copper-like intermediate break down and form the new bond. This explains why BF3 makes these reactions so much faster experimentally. These computational tools are, well, they're like having X-ray vision for molecules. They allow chemists to not just observe reactions, but to actually see the invisible dance of electrons and atoms, explaining why these reactions are so selective and how additives work.
That's truly remarkable, seeing the invisible mechanism. Now, another critical area in synthesis, especially for pharmaceuticals, is creating just one specific mirror image form of a molecule. That's an antioselectivity, right?
Right.
How do organocopper reagents achieve this?
Right. Achieving an antioselectivity is absolutely vital in drug synthesis. Often only one mirror image form, one enantiomer of a drug, has the desired biological activity. The other enantiomer can be inactive or in some cases even harmful.
So you need just one.
You need just one. Organocopper reagents can achieve this enantioselectivity in, broadly speaking, 2 main ways. One way is by using chiral auxiliaries. These are existing chiral molecules that are themselves non-superimposable on their mirror image, that are temporarily attached to the reactant. They act like a chiral handle, guiding the incoming copper reagent to attack one specific face of the molecule, leading to one enantiomer preferentially.
A temporary guide.
A temporary guide, which you then remove. The other method, which is often more desirable because it's potentially more efficient, is by using chiral ligands. These are small chiral molecules that bind directly to the copper metal itself, creating a unique 3-dimensional chiral pocket around the active site.
The environment around the copper is chiral.
Exactly. This chiral environment forces the reaction to proceed in a way that predominantly forms one specific mirror image product. Chemists have designed many clever chiral ligands, often based on phosphorus or nitrogen, that give very high levels of enantioselectivity in copper-catalyzed reactions, especially conjugate additions.
That's key for making modern medicines.
Mm-hmm.
What about joining 2 aromatic rings together? Those benzene-like rings are common building blocks.
Right. That brings us to aryl-aryl coupling using organocopper reagents. A classic older example is the Ullmann coupling. Traditionally, this involved heating aromatic halides, like iodobenzene, with a copper-bronze alloy at very high temperatures.
High temperature sounds harsh.
It was often harsh and typically only worked well if the aromatic rings had specific electron withdrawing groups attached. Modern chemistry has improved this significantly. By using soluble copper salts, often things like copper triflate, the reaction can be done at much lower temperatures and under more controlled, homogeneous conditions.
More practical now.
Much more practical. And for creating unsymmetrical birals where the two coupled aromatic rings are, different chemists can make a mixed copper reagent, maybe a diaryl cupret with two different aromatic groups attached. These can then react, often triggered by mild oxidation, to form the desired two-ring product. It's a precise way to stitch together complex molecular structures containing multiple aromatic rings.
Wow, what an incredible range of transformations copper can facilitate. So, to quickly recap before we move to palladium, what are the key synthetic reactions we should remember for organocopper reagents?
Okay, a quick summary. Organocopper reagents are incredibly versatile for, first, various types of coupling reactions, allowing you to join alkyl, alkenyl, or aryl groups together, often using those clever mixed cuprates to transfer only the desired piece. Second, allylic coupling, which often proceeds with that useful shift of a double bond, the SN2 reaction. Third, epoxide ring opening, which creates new alcohol structures with very precise control over regiochemistry and stereochemistry. And fourth, their real signature move, conjugate additions to unsaturated carbonyl compounds, enones, enoates, etc., taking advantage of their soft nucleophilicity.
And those can be done in sequence too, right?
Yes, absolutely. These conjugate additions can even be done in sophisticated tandem sequences, where the initial enolate product of the conjugate addition is immediately trapped and reacted again with another electrophile, all in the same reaction flask. Builds complexity quickly.
Okay. In essence, they provide surgical control over carbon bond formation, making them indispensable tools in the synthetic chemist's toolbox. Right. Let's move on to our second star player, palladium. If copper is maybe a master builder painstakingly adding delicate pieces, then palladium is often described as a true maestro in organic synthesis, renowned for its incredible catalytic power and its ability to orchestrate complex molecular ballets.
Absolutely. That's a great way to think about it. The real elegance of palladium chemistry is that in most of its useful applications, you don't use up large stoichiometric amounts of palladium. Instead, the active organopalladium species are generated in situ right there in the reaction mixture and then continuously regenerated throughout the process.
The catalytic cycle again.
The catalytic cycle in full force. This allows a tiny amount of this precious and frankly expensive metal to do a huge amount of work, which is why it's so economically and environmentally beneficial, especially when you think about large-scale industrial production of pharmaceuticals or materials.
Makes sense. So what are the core moves in palladium's repertoire? What kinds of intermediates does it form?
Palladium's chemistry revolves around several key types of intermediates. First, it readily forms pi-alkene complexes. When a carbon-carbon double bond, an alkene, encounters a palladium species, they form a temporary bond where the alkene's pi electrons coordinate to the metal. This coordination activates the alkene, making it susceptible to attack by other molecules, often nucleophiles. Depending on the conditions, this can lead to different outcomes, like adding hydrogen across the double bond, or maybe substituting a hydrogen on the double bond with something new.
Okay, pi-alkene complexes. What else?
Second, we have the extremely important pi-allyl complexes. These are incredibly versatile intermediates in palladium chemistry. They typically form when palladium interacts with allylic compounds. Remember, those molecules with a double bond next to a carbon that has a leaving group, like an acetate or a halide. These pi-allyl palladium complexes are moderately electrophilic, meaning they're somewhat electron poor at the allyl carbon atoms and ready to react with nucleophiles, those electron-rich species we talked about with copper.
So they get attacked by nucleophiles.
Exactly. This allows for allylic substitution reactions, where the original leaving group is effectively replaced by the incoming nucleophile, often a carbon-based one, forming a new carbon-carbon bond.
Very useful for building chains.
Very useful. A third, and perhaps the most important general process, involves oxidative addition. This is a cornerstone reaction, particularly for palladium-0. Palladium-0, which has a specific electron configuration, D10, similar to copper, readily inserts itself into carbon-halogen bonds, like CBr, Ci, or similar bonds like carbon triflate.
Inserts itself into the bond.
Yes, it breaks the CX bond and forms two new bonds, a CPD bond and a PDX bond. This forms a new carbon-palladium sigma bond and increases palladium's oxidation state from 0 to +2. These sigma-bonded organopalladium species are then highly reactive intermediates. They can go on to react with alkanes, like in the Heck reaction, or react with other organometallic reagents in cross-coupling reactions, forming new CC bonds.
Oxidative addition seems central.
It's absolutely central to many of palladium's most powerful catalytic cycles. And finally, palladium can also form acyl-palladium intermediates. These are key for making ketones and other related carbonyl compounds like esters or amides. They can form when acyl halides, RCOCl, react with palladium, or sometimes when an existing organopalladium species reacts with carbon monoxide CO gas through an insertion reaction. Once formed, these acyl-palladium intermediates can easily react with other organic groups, often from another organometallic reagent, to form new ketones, or react with alcohols or amines to form esters or amides.
Okay, so palladium has many tricks up its sleeve. Pialkanes, piolyls, oxidative addition products, acyl intermediates. What are the overarching principles that govern all these different types of organopalladium chemistry?
There are a few crucial principles that run through most of palladium catalysis. First, most palladium reactions occur in the presence of phosphine ligands, ligands like triphenylphosphine, PPH3, or more complex phosphines.
The phosphines again, like with copper.
Well, yes and no. They're even more ubiquitous and arguably more crucial in controlling palladium chemistry. These phosphines are like molecular hands that grip the palladium atom. They profoundly influence its reactivity, its stability, its solubility by controlling the electron density and the space around the metal center. Choosing the right phosphine ligand is often key to getting a reaction to work well or work at all.
Ligand choice is critical.
Oh, absolutely critical. Second, the carbon-palladium sigma bond is relatively weak compared to, say, a carbon-carbon bond. And it's particularly prone to breaking if there's a hydrogen atom on the carbon atom next to the one bonded to palladium, what we call a Ba hydrogen. This means alkyl palladium species with a Ba hydrogen tend to readily break down via a process called beta hydride elimination.
Beta elimination. Sounds important.
It is. It forms a new carbon-carbon double bond in the organic fragment, releases HX like HBr, and usually regenerates the active palladium xeric catalyst, or a palladium hydride species. This tendency is actually a key productive step in many palladium reactions, like the Heck reaction, as it's how the final product is often released from the metal.
So it's not always an unwanted side reaction.
Not at all. It's often the desired final step in the catalytic cycle. And finally, just like we saw with copper, palladium species that end up with two organic groups attached, RPDR, tend to readily undergo reductive elimination. Those two organic groups, R and R, combine to form a new R bond, usually the desired carbon bond in cross-coupling reactions, and the palladium returns to its catalytically active lower oxidation state, usually PD0, ready to start the cycle again.
Okay, so oxidative addition may be insertion or transmetallation, then reductive elimination or beta elimination. That sounds like the core cycle.
That's the essence of many, many palladium catalytic cycles. The metal acts like a switch, changing its oxidation state, forming different types of bonds, coordinating and activating molecules, and guiding them towards specific products before regenerating itself.
Right. Let's look at one of its signature industrial reactions then, the Wacker reaction.
Indeed. The Wacker reaction, or Wacker process, is a cornerstone of industrial organic chemistry. It catalytically converts ethene simple ethylene gas into acetaldehyde, which is a key industrial chemical.
Ethene to acetaldehyde. How does it work?
The magic here involves palladium-2 activating the ethene double bond towards attack by water. Water adds across the double bond in a step called oxypalidation. This forms a hydroxyethyl palladium intermediate. This intermediate then undergoes that characteristic beta hydride elimination we just talked about. This eliminates the palladium as PD0 and a proton H+, initially yielding vinyl alcohol, which rapidly rearranges or tautomerizes to the stable acetaldehyde product.
And it's catalytic in palladium.
Yes, and that's the brilliance. You only need a catalytic amount of the expensive palladium salt. The trick is using helper reagents, typically copper-2, chloride CuCl2, and oxygen O2, to reoxidize the spent palladium-0 back to the active palladium statesite. This reoxidation allows the catalytic cycle to continue, so the net reaction effectively consumes only the starting alkene, ethene, and oxygen, making it very economical for producing acetaldehyde on a massive scale.
Clever use of copper as a co-catalyst there.
Very clever. It keeps the palladium cycle turning over. Now, the Wacker reaction is remarkably sensitive to the type of alkene used. For example, simple ethene reacts fastest, then propene, and then increasingly bulky alkenes react much slower.
So size matters. Sterics.
It strongly suggests that steric factors, the physical size and shape of the molecule, play a big role, perhaps more than just electronics, in how quickly the alkene coordinates to palladium and reacts. The addition step itself, the oxypalladation, typically happens with syn addition. That means the water, as OH, and the palladium add to the same face of the double bond.
Syn addition.
Usually. However, even a simple change like increasing the concentration of chloride ions in the solution can surprisingly shift the reaction mechanism so that you get anti-addition, where they add from opposite faces. Shows how subtle changes affect the pathway.
Fascinating. Conditions can dramatically change the outcome. What about the regiochemistry for terminal alkenes, ones with the double bond at the end? Do you get aldehydes or ketones?
Good question. For most simple terminal alkenes, like propene or 1-butene, the Wacker oxidation typically forms methyl ketones. So propene gives acetone, 1-butene gives 2-butanone.
Ketones, not aldehydes. Why?
This happens because the initial attack of water, or the oxypalladation step, preferentially occurs at the more substituted carbon of the double bond, consistent with the palladium-2 acting somewhat like an electrophile. The oxygen ends up on the internal carbon.
Markovnikov type addition.
Exactly. It follows Markovnikov's rule, generally. However, chemists can tune this. For instance, using T-butanol as a co-solvent can sometimes increase the amount of aldehyde formed from terminal alkenes. It likely involves forming intermediate enol ethers, so you can exert some control over the outcome.
Control is always good.
Always. The Wacker reaction is also extensively used in multi-step synthesis, sometimes allowing for the selective oxidation of one double bond over another if they have different steric accessibility. Maybe one is hidden inside a complex molecule.
Swern.
And palladium-2 can even induce intramolecular Wacker-type reactions. If you have a molecule with both a double bond and a suitable nucleophile, like an alcohol or carboxylic acid elsewhere in the chain,
They can react together.
yes, the internal nucleophile can attack the palladium-activated alkene, leading to cyclization, forming a ring. This is used to make things like unsaturated lactones or cyclic ethers, very powerful for building complex ring systems.
Okay, so the Wacker reaction is powerful for adding oxygen to molecules, making aldehydes and ketones, and even rings. What about adding new carbon chains? Where does palladium shine there?
That brings us to palladium's pivotal role in allelic substitutions. Those pyrrole palladium species we mentioned earlier are incredibly versatile intermediates for this. They essentially allow you to replace a leaving group, like acetate, carbonate, halide, on an allelic system, remember, CCCX, with a new carbon chain, usually from a carbon-based nucleophile.
So CC bond formation at the allelic position.
Exactly. This is especially effective with relatively stable carbon nucleophiles, like those derived from malonate esters or other stabilized enolates. And again, the key is catalysis. These pyrrole complexes are typically generated in situ using just a catalytic amount of a palladium-0 source, often something like PDA, PPH34, or generated from PTAC2 with phosphine ligands. The active PD0 is continuously regenerated in the cycle.
What about control? If the starting allelic system is unsymmetrical?
Yes. Controlling the regiochemistry, which end of the allelic system gets substituted, and the stereochemistry, the 3D orientation, is absolutely crucial for unsymmetrical systems. Interestingly, sometimes the same product mixture is obtained even if you start from different isomers of the allelic starting material. This suggests that the intermediate pyrrole palladium complex itself can rapidly isomerize or equilibrate before the nucleophile attacks.
The intermediate scrambles?
It can, yes. The palladium can sort of slide between the two ends of the allyl system. However, when you use special chiral phosphine ligands, this rapid equilibration can actually be beneficial. The system might equilibrate to the most stable chiral pyrrole complex, and then the subsequent attack by the nucleophile can be highly stereoselective, producing mostly one specific mirror image product.
So the ligand controls the final step stereochemistry.
Often, yes. The nucleophile's attack itself can happen in different ways mechanistically. Soft nucleophiles, like malonates, are believed to attack from the face opposite to the palladium, external attack, often leading to overall inversion of stereochemistry at the carbon. Whereas harder nucleophiles might be delivered from the same face as the palladium, internal transfer, leading to overall retention of stereochemistry. It's complex and depends on the specific nucleophile and conditions.
Seems like conditions are always key.
Always. For example, just adding iodide ions to the reaction mixture can sometimes dramatically switch the regioselectivity, favoring attack at one end of the ally system over the other. It's thought the iodide becomes a ligand on palladium and changes its behavior, and these palladium-catalyzed alylation reactions are excellent for forming rings, too, especially medium and large rings, which can be tricky otherwise. Very powerful tools for building complex structures.
Okay, so palladium guides both oxygen additions, Wacker, and carbon additions, allylic substitution. Now let's move to one of the most famous palladium reactions of all, the Heck reaction.
Ah, yes, the Heck reaction. It's absolutely fundamental. Awarded the Nobel Prize in Chemistry in 2010, along with Negishi and Suzuki for related cross-couplings.
A Nobel Prize winner, what does it do?
The Heck reaction is primarily used for creating new carbon-carbon bonds, specifically by coupling aryl halides, or vinyl halides, or triflates, with alkenes. It effectively substitutes a hydrogen atom on the alkene with the aryl or vinyl group from the hal.
So attaching aromatic rings or vinyl groups directly onto double bonds.
Exactly. It's incredibly broad in scope, working with many types of alkenes, simple ones already substituted with aromatic rings, and especially alkenes bearing electron-withdrawing groups like esters, acrylates, nitriles, or amides. Many Heck reactions use palladium acetate, PDOAC2, as the pre-catalyst, with the active palladium species being generated right there in the reaction flask, often by reduction with a phosphine ligand or an amine base. And those phosphine ligands are, again, usually crucial for the reaction's success. Ligands like triphenylphosphine or bulkier ones like trietolylphosphine are common.
Right. Let's break down the mechanism of the Heck reaction. What are the core steps in that catalytic cycle?
Okay, the generally accepted catalytic cycle for the Heck reaction starts with 1. Oxidative addition. The aryl or vinyl halide, or triflate, RX, adds to the active palladium species. This forms an organopalladium-2 intermediate, RPD2X.
Step 1, oxidative addition.
Step 1. Then 2, alkene coordination and insertion. The resulting RPDX intermediate coordinates to the alkene reactant. Following coordination, the R group attached to palladium migrates and inserts into the alkene double bond, forming a new carbon-carbon sigma bond. This is called migratory insertion or carbopalladation.
Okay, coordination, then insertion. Forms the CC bond.
Forms the crucial CC bond, yes. This insertion step typically occurs with syn stereoselectivity, meaning the R group and the palladium add to the same face of the alkene double bond. Then, 3, beta hydride elimination. The new alkyl palladium intermediate, which now has that necessary Bow hydrogen, undergoes beta hydride elimination. A hydrogen atom from the adjacent carbon is transferred to the palladium, the CPD bond breaks, and a new double bond forms in the organic product. This step also usually occurs with syn stereoselectivity regarding the departing H and PD.
Beta elimination releases the product.
It releases the final substituted alkene product, and it forms a palladium hydride species, HPDIX. Finally, 4. Regeneration of catalyst. This palladium hydride species eliminates HX, like HBr or HI, with the help of a base that's always added to the reaction mixture. This regenerates the active palladium dirocatalyst, ready to start the cycle all over again.
Base is needed to neutralize the acid formed.
Exactly, and to help regenerate the PD0. So, oxidative addition, migratory insertion, beta hydride elimination, regeneration, that's the core loop. Now, there are some fascinating mechanistic nuances and variations depending on the exact conditions, ligands, and substrates.
Such as?
Well, sometimes under certain conditions, particularly with PDOAC2, phosphines, and amine bases, an anionic mechanism might be at play, where the active palladium species is actually a negatively charged complex, which can affect reactivity. Other times, especially when using triflates as the leaving group or adding silver salts, a cationic mechanism might be favored. Here, the intermediate palladium species becomes more positively charged, cationic, making it more electrophilic and potentially reacting faster or differently, especially with electron-rich alkenes.
So the charge on the palladium matters.
It can significantly influence the pathway and outcome, even especially ring with the phosphine ligand can form and act as highly active catalysts.
Okay. What kinds of modifications have chemists made to the Heck reaction over the years to make it even more versatile or practical?
Oh, many, many modifications. Chemists are always optimizing. Adding silver salts, as I mentioned, can help activate the halides starting material, particularly chlorides, making the initial oxidative addition easier. Using simple inorganic bases like sodium or potassium carbonate, often combined with phase transfer catalysts, allows for very mild reaction conditions, which is great for sensitive molecules.
Milder is better.
Usually, yes. They've developed solid-phase catalysts, where the palladium or the phosphine ligand is attached to a polymer bead. This makes it much easier to separate the catalyst from the product afterwards, just filter it off. Important for purification and catalyst recycling. Traditionally, aryl chlorides were quite unreactive in the Heck reaction compared to bromides or iodides. But new generations of highly active catalysts, often using very bulky, electron-rich phosphine ligands or sometimes N-heterocyclic carbenes, NHCs, as ligands, have made aryl chloride couplings much more feasible. That's a big deal because chlorides are often cheaper and more readily available.
Opens up more starting material.
Exactly. And perhaps one of the most significant developments has been the ability to carry out Heck reactions effectively without any added phosphine ligands at all.
No phosphines. How does that work?
It often involves using just palladium acetate, maybe with a base and a phase transfer salt. The exact nature of the active catalyst in these phosphine-free conditions is still debated. It might involve tiny palladium nanoparticles or clusters acting as a catalyst or a reservoir for soluble species, but it can work remarkably well and simplifies the reaction setup and workup considerably.
Simpler is often better, too.
Definitely. Now, controlling the regiochemistry of the Heck reaction, where exactly the new aryl or vinyl group attaches to the alkene, is also important.
Right. Which hydrogen gets replaced?
It's determined by that beta hydride elimination step. If the intermediate formed after insertion has multiple different hydrogens available, you might get a mixture of products where the new double bond forms in different positions. Sometimes the double bond can even migrate further along a chain due to reversible elimination and readdition of the palladium hydride.
Can you control it?
To some extent, yes. Substituents on the alkene play a big role. Electron-withdrawing groups, like esters or nitriles, usually direct the incoming aryl group to the beta position, further from the group, and the double bond forms between the alpha and beta carbons. Electron-donating groups, like alkoxy groups, can be less predictable. However, the choice of ligand can also influence regioselectivity. Certain bulky phosphines or specific bidentate two-armed phosphine ligands can sometimes favor addition at the alpha position, closer to the substituent, possibly by influencing the stability of intermediates or favoring that cationic pathway. Computational studies have been vital here too, helping us understand the electronic and steric factors that govern where the palladium adds and from where the hydrogen leaves.
Okay, that's a lot of power and control packed into one reaction. What are some of the practical synthetic applications where the Heck reaction really shines?
Oh, it's used everywhere in complex molecule synthesis. It shows excellent selectivity, for instance, reacting an aryl iodide in the presence of an aryl bromide on the same molecule.
Chemoselectivity.
Right. It works well with vinyl triflates, which are easily made from ketones. We've seen examples of incredibly high catalyst efficiency needing only tiny amounts of catalyst, especially with some of those specialized paladocycle catalysts. We've also seen elegant examples of sequential Heck reactions being used. For instance, in synthesizing a complex drug target, chemists use the reactivity difference between an iodide and a bromide on the same starting molecule. They performed one Heck reaction selectively at the iodide position, then changed conditions or catalysts slightly to perform a second, different Heck reaction at the bromide position. A very sophisticated way to build complexity stepwise.
Wow.
And perhaps the most impactful application area is in intramolecular Heck reactions.
Forming rings.
Forming rings, exactly. If the aryl halide and the alkene are part of the same molecule, the Heck reaction can stitch them together, forming a new ring. This is incredibly widely used for constructing complex polycyclic structures found in many natural products and pharmaceuticals. There are countless examples, key steps in the synthesis of anti-cancer agents like camptothecin and Taxol precursors, alkaloids like morphine analogs, and other biologically active compounds like galantamine, which has been investigated for Alzheimer's disease. The ability of the intramolecular Heck reaction to forge complex ring systems, often with high stereo control, is a testament to its incredible synthetic utility.
That's incredible. Building rings like that is so fundamental. But palladium's talents don't stop there, do they?
Yeah.
It's also at the heart of what are called cross-coupling reactions, which, as you mentioned, shared that Nobel Prize and have truly transformed organic synthesis.
You're absolutely right. If the Heck reaction connects aryl vinyl groups to alkanes, then cross-coupling reactions connect aryl vinyl groups, or sometimes alkyl groups, to other organic groups derived from organometallic regions. This is perhaps the most broadly impactful area of palladium chemistry in modern synthesis. It has arguably revolutionized how chemists think about and execute the construction of complex molecules, particularly for pharmaceuticals and materials science.
So connecting two different organic pieces using palladium.
Precisely. The core concept is forming new carbon carbon bonds between one partner, typically an aryl or vinyl halide or triflate, R1X, and a second partner, which is an organometallic reagent, R2M, where M is often lithium, magnesium, grignard, zinc, tin, boron, or silicon. The palladium catalyst brings R1 and R2 together to form R1R2. It's incredibly general for making sp2-sp2 bonds, like connecting two aromatic rings to make birols, sp2-sp bonds, connecting an aromatic ring to a triple bond, making enenes, forming conjugated dienes and polyenes.
What about connecting to normal alkyl groups, sp3 carbons?
That's historically been trickier, making sp2-sp3 bonds. The challenge is that the intermediate alkyl palladium species, RPDX, are often very prone to that beta hydride elimination pathway before they can couple with the second partner. However, enormous progress has been made in recent years using specific ligands and conditions to enable St2-sp3 couplings and even sp3-sp3 couplings much more reliably. It's a very active area of research.
Okay. How does the catalytic cycle of a generic cross-coupling reaction work? What are the basic steps involved?
The basic steps in the palladium-catalyzed cross-coupling cycle are elegant and remarkably similar across the different named reactions, Zucchi, Still, Negishi, etc. It usually involves three key stages. One, oxidative addition. Just like in the Heck reaction, the aryl or vinyl halidotriflate, R1X, adds to the palladium catalyst, forming an organopalladium-2 intermediate, R1PDX.
Same first step.
Same first step. Then, 2, transmetallation. This is the step that's different from Heck. Here, the organic group R2 from the second organometallic region, R2M, is transferred from its metal M to the palladium center, displacing the halide or triflate X. This forms a diorganopalladium-2 intermediate, R1PDDR2.
Swapping the group onto palladium, transmetallation.
Exactly, metal-to-metal transfer. Finally, 3, reductive elimination. This diorganopalladium-2 intermediate, R1PDR2, undergoes reductive elimination. The two organic groups, R1 and R2, combine to form the new desired carbon-carbon bond, R1R2, which is the product. And crucially, this step regenerates the catalytically active palladium species, allowing the cycle to repeat thousands or millions of times.
Oxidative addition, transmetallation, reductive elimination, the core loop.
That's the fundamental catalytic cycle for most palladium cross-couplings. Of course, the ligands around the palladium, the nature of the organometallic region M, the base or additives used, they all play crucial roles in controlling the rates of these steps, the stability of the intermediates, and the overall success of the reaction.
Right. Let's look at a few specific famous cross-coupling reactions. What about the Sonogashira reaction for making carbon-carbon triple bonds? Seems important for alkynes.
The Sonogashira reaction is indeed a key method for forming carbon bonds between an aryl or vinyl halidotriflate and a terminal alkyne, a molecule with a CHN group. It leads to products called conjugated enenes or dienes, which are important structures.
How does that one work? What's the organometallic part?
The typical Sonogashira recipe uses a palladium catalyst, often PD, PPH34 or similar, but it also requires a copper I, salt, as a co-catalyst, usually copper I, iodide, CuI, and an avenine base like triethylamine or disopropylamine.
Copper again, like in the Wacker reaction, but different role.
Different role here, yes. The amine base first deprotonates the terminal alkane, RCCH, to make it nucleophilic. Then the copper salt reacts with this deprotonated alkane to form a copper acetylide intermediate, RCCQ. Meanwhile, the aryl vinyl halide undergoes oxidative addition to the palladium catalyst to form R1PD by X. Then, the copper acetylide transfers its alkynyl group, RCCC, to the palladium center via transmetallation, displacing the X group. This gives R1PD ICCR. Finally, reductive elimination occurs, forming the new CC bond, R1CCR, and regenerating the PD0 catalyst. The copper acts as a facilitator for getting the alkane group onto the palladium.
So copper helps the transmetallation step here.
Exactly. Now, what's exciting is that in recent years, chemists have developed very effective copper-free Sonogashira conditions, often using specific bulky phosphine ligands or NHC ligands on palladium, along with stronger bases. This avoids using copper, which can sometimes cause side reactions like alkane dimerization, Glaser coupling, and simplifies purification. It's a significant improvement.
That's a huge leap, no copper needed, if you choose the right conditions. What about directly attaching an aromatic group to an enolate? You mentioned that was historically difficult. Has palladium helped there?
Yes, tremendously. Directly forming a bond between an aromatic ring and the alpha carbon of a ketone or ester via its enolate, what's called alpha arylation, was a major challenge for a long time. Palladium-catalyzed cross-coupling has provided powerful solutions.
Why was it hard before?
Enolates are good nucleophiles, but they can also act as bases, and they can react at oxygen instead of carbon. Getting clean C aerolation was tricky. Palladium catalysis changed the game, using aryl halides or triflates as the aromatic partner and generating the enolate of the ketone or ester using a suitable base. Palladium catalysts, particularly those bearing very bulky electron-rich phosphine ligands like tritibutylphosphine or specific biryl phosphine ligands like Buchwald's ligands or NHC ligands, can effectively couple the two pieces together.
Specific ligands are key again.
Absolutely essential for this transformation. These bulky ligands are thought to promote the crucial reductive elimination step, which forms the CC bond, over competing side reactions like beta hydride elimination if the enolate has beta hydrogens. This method has been applied to a wide range of challenging substrates, like ketones, esters, amides, even nitriles. It's used to make important pharmaceutical intermediates, for example, alpha-aryl propanoic acids, which are the structural core of many common NSAID pain relievers like ibuprofen or naproxen. It shows how palladium catalysis can create precise, medicinally relevant structures in a way that was previously very difficult or impossible.
It sounds like palladium has truly revolutionized how chemists approach making these kinds of carbon bonds. Another big name in cross-coupling is the Still reaction. Tell us about that one. What metal does it use besides palladium?
The Still reaction is another incredibly important and widely used palladium-catalyzed cross-coupling method. In this case, the organometallic coupling partner is an organostanin, an organic compound containing a tin atom, usually with alkyl groups like tributyltin, SNBU3, attached, so R2, SNBU3.
Tin compounds, are they easy to handle?
They are generally stable, often isolable compounds, which is an advantage. They can be prepared with a wide variety of R2 groups, aryl, vinyl, allokynyl, even some alkyl groups. The Still reaction couples these organostanins, R2-SNBU3, with organic halides or triflates, R1X, using a palladium catalyst, typically with phosphine ligands like PPH3 or sometimes triphenylursine as
Arsenic.
Yes, triphenylursine is sometimes a preferred ligand for still couplings. The reaction is remarkably general, working with many types of halides, aryl, vinyl, benzyl, allyl, and transferring various groups from tin. There's a general reactivity order for group transfer from tin. Alkynyl groups transfer fastest, then vinyl, then aryl, then allobenzyl, and finally alkyl groups transfer slowest. This selectivity is useful if you have multiple groups on the tin. You can selectively transfer just the most reactive one.
Useful selectivity. Does it need additives?
Sometimes. Copper I's, like QI, can be added as co-catalysts, particularly for aryl couplings, to speed up the reaction, possibly by facilitating the transmetallation step. Also, adding salts like lithium chloride, LiCl, can sometimes accelerate the reaction, especially when using triflates, perhaps by making the palladium intermediates more reactive. Mechanistically, it follows the standard cycle. Oxidative addition of R1X to PD0, then transmetallation where R2 transfers from tin to palladium, and finally reductive elimination to form R1R2 and regenerate PD0. The exact details of the transmetallation step can be complex and depend on ligands and additives.
What about stereochemistry, if you have double bonds?
That's a major strength of the Still reaction. It's highly stereospecific. If you start with a specific E or Z configuration in your vinyl stannin or vinyl halide, that precise configuration is usually retained in the final coupled product. This is incredibly valuable for building complex molecules like polyamines found in natural products, like carotenoids or retinoids, where the exact geometry of the double bonds is critical for their biological function.
Retaining the geometry. Very powerful.
Very powerful. It also tolerates a wide range of other functional groups in the molecule. Esters, nitriles, ketones, amides often survive the reaction conditions untouched. Although the tin byproducts, like B3SNX, can be toxic and sometimes difficult to remove completely, which is a drawback compared to some other methods.
Oh, the waste products.
Yes, that's always a consideration in green chemistry. Despite that, the Still reaction has been instrumental in synthesizing incredibly complex structures, including large macrocyclic rings found in potent natural products like amphidenolide or rapamycin. The ability to form CC bonds reliably under relatively mild conditions made it a go-to reaction for many years. It can even be used to make ketones by coupling organostanins with acyl chlorides.
Fascinating versatility. And finally, let's look at another incredibly powerful palladium-catalyzed cross-coupling, perhaps the most widely used in modern synthesis today, the Suzuki reaction. What metal does that involve?
The Suzuki reaction, or Suzuki-Miura coupling, is indeed a cornerstone of modern organic synthesis, probably the most frequently used cross-coupling reaction in both academia and industry today. In the Suzuki reaction, the organometallic coupling partner is an organoboron compound. Most commonly, these are boronic acids, R2BO, or related boronate esters, R2BO or 2.
Boron compounds, why are they so popular?
Several reasons. First, boronic acids are often stable, crystalline solids that are relatively easy to handle and store. Many are commercially available or readily prepared. Second, the boron-containing byproducts, like boric acid, BOH3, are generally considered much less toxic and more environmentally benign than the tin byproducts from the still reaction. They're often water-soluble and easier to remove during workup.
Greener chemistry, that's a big plus.
A huge plus. Third, the Suzuki reaction conditions are often quite mild and tolerant of a wide range of functional groups, similar to the still reaction.
How does the Suzuki mechanism work? Still the same core cycle?
Yes, the overall catalytic cycle is very similar. Oxidative addition of the halidotriflate, R1X to PD0, then transmetallation of the R2 group from boron to palladium, and finally reductive elimination to form R1R2 and regenerate PD0. A key difference or requirement for the Suzuki reaction, especially when using boronic acids, is the presence of a base.
Find a base.
The base, like sodium carbonate, potassium phosphate, cesium carbonate, or even hydroxides, is believed to activate the boronic acid for the transmetallation step. It likely forms a more nucleophilic boronate species like R2BOH3, which transfers the R2 group to the palladium center more readily than the neutral boronic acid itself. The choice of base can be critical for the reaction's success.
Base activates the boron part.
That's the generally accepted rule. The Suzuki reaction couples aryl or vinyl halidestriflates with aryl, vinyl, or even some alkyl boron reagents. Still, it's highly stereospecific for reactions involving vinyl partners. The double bond geometry is retained. This makes it excellent for synthesizing specific isomers of diaretimine or other conjugated systems.
You mentioned alkyl groups. Can Suzuki couple regular saturated carbons?
Yes, and this has been a major area of advancement. While coupling simple alkyl halides is still challenging for palladium due to side reactions, coupling alkyl-boron reagents, often derived from hydroboration of alkenes using reagents like 9-BBN, with aryl or vinyl halides has become quite reliable using specialized catalysts and conditions. This provides a crucial route to sp2-sp3 bonds, overcoming the beta hydride elimination problem to a significant extent. Specific bulky phosphine ligands or NHC ligands have been key here too.
So it bridges the gap to alkyl groups better.
It does, much better than many earlier methods. The Suzuki coupling has found incredibly widespread use in the synthesis of extremely complex molecules. It's often used as a key stitching reaction to link large, complex fragments together late in a synthesis. We see it used in the synthesis of anti-cancer drugs like apothalone, marine natural products like paletoxin fragments, and countless pharmaceutical candidates. It's also robust enough for large-scale industrial applications. There are published examples of Suzuki couplings being run on hundreds of kilograms scale to produce drug intermediates, often with very high yields and catalyst efficiency. It truly highlights how these academic discoveries translate into real-world impact. It can even be adapted to make ketones from acyl chlorides or other activated carboxylic acid derivatives.
Wow, what an incredible journey through the world of transition metal catalysis. We've seen how copper and palladium, in their various forms and through these precise mechanisms, are truly the unsung heroes behind countless complex molecules we rely on.
Indeed, it's quite a story. From the subtle dance of electron-rich copper in conjugate additions and epoxide openings, where it acts as that soft nucleophile with almost surgical precision, to palladium's incredibly versatile choreography in Wacker oxidations, Heck arylations, and that vast, powerful array of cross-coupling reactions like Sonobashira, Still, and especially Suzuki. These metals truly enable chemists to build molecular architectures with just astonishing control and efficiency.
What really stands out to me is how a deep understanding of the underlying mechanisms, those oxidative additions, reductive eliminations, transmetallations, beta eliminations, how that knowledge allows chemists to actually design new catalysts and really fine-tune reactions for specific outcomes, creating everything from life-saving drugs to advanced materials for electronics or polymers. The sheer power of a catalytic process using just a tiny pinch of metal to create massive impact is truly remarkable. It's a testament to human ingenuity in mimicking and often enhancing nature's own synthetic strategies.
It absolutely highlights that. Even in these highly specialized fields like advanced organic synthesis, it's still the fundamental principles of electron flow, orbital interactions, and atomic choreography that drive innovation. The constant pursuit of understanding the why behind the what. Why does this reaction work? Why is it selective? How can we make it better? That's what pushes the boundaries of what's possible in the lab, and ultimately that shapes the medicines we take and the materials that build the world around us. The ability to precisely control the formation of carbon bonds using these transition metals really represents a pinnacle of synthetic ingenuity.
And that's our deep dive into the fascinating world of transition metals in organic synthesis, focusing on our two stars, copper and palladium. We really hope you've had some aha moments along the way, perhaps gained a shortcut to being well-informed on this topic,
Hopefully.
and maybe even sparked a new curiosity about the incredible chemistry that shapes our modern world. Until next time on The Deep Dive, keep digging deeper.